So this is section 3D, or 3E, excuse me, and we're continuing to look at optimization problems. We want to find in this example 4 here, the point on the graph of f of x equals the square root of x that is closest to the point 4, 0. So let's see what we're talking about here. We've got the graph f of x equals the square root of x, which basically looks like that. And then the point 4, 0 would be right there. So our goal is to figure out which point up here would be as close as possible. Call that point P for right now. I want to find that point that's as close as possible to the point 4, 0. So if I need to phrase this in the language that we're using, I needed an objective function. I need something that I'm trying to maximize or minimize. In this case, it's actually this distance between these 2 points that I'm trying to minimize. I want them to be as close as possible. So if I just call that distance, let's call it capital D, my goal is to minimize the distance D. And to write down a formula for D, I'll think of this point here as 4, 0, and this is just some point x, y on the graph. And I'll use my distance formula. Distance is the square root of y2 minus y1 squared plus x2 minus x1, so x minus 4 squared. Or in this case, the square root of y squared plus x squared minus 8x plus 16. All right, we have a familiar problem. We've got too many variables, both x and y. So in this case, I'm going to need a constraint, but I think the constraint is actually already here. Notice that this point had to be on this graph. So in fact, my constraint is, in order for the point to be on the graph, y has to be equal to the square root of x. So I'm going to plug that in right now. And that means I can write my distance function as the square root of the square root of x squared plus x squared minus 8x plus 16. And ultimately, I want to minimize the function d equals, I can get rid of the square root and the square here, and then just combine those two terms. So I actually end up with the square root of x squared minus 7x plus 16. All right. I'll do my first derivative test. So I need d prime. And I probably should have done this in the last step, but I'm going to sneak it in now. Instead of thinking about that as a square root, let's think about that instead as a 1/2 power. So I end up with 1/2 x squared minus 7x plus 16 to the negative 1/2. And then my chain rule, the derivative of what's inside would be 2x minus 7. So that's really 2x minus 7 on top, and on the bottom 2 times the square root of x squared minus 7x plus 16. And I'd like to know where that's equal to 0. If I multiply both sides of this equation by the denominator, the left-hand side will still be 0, but it'll cancel out the denominator on the right. So I get 0 equals 2x minus 7. 2x is 7, so x would be 3.5. Again, just for the sake of time and as well as space, I'm going to leave it to you to go ahead and try that little first derivative test. You can put the little number line together if you want to show that you really do have a minimum. I'm going to skip that step just to keep these videos moving a little bit, but I challenge you to do that on your own. So my goal was to find the point that was closest. I now know the x value. To get the y value, I just plug 3.5 back into my constraint. I can get a decimal, get a decimal approximation for that if I want to. It's about 1.87. So the point on the graph, 3.5, 1.87, is the point that's closest to 40 while still lying on that original graph. All right, let's take a look at number 5. I want to find the dimensions of the rectangle with the largest possible area, so here we go with an area problem again, that can be drawn in the first quadrant under the line x plus 2y equals 6. So let's see here. I want to stick with my first quadrant, and the line x plus 2y equals 6. X-intercept, if y is 0, would be 6. And the y-intercept, if x is 0, would be 3. So I'm looking at this line right here, at least the part of it that's in the first quadrant. My rectangle has to be underneath that line and stay in the first quadrant. So my rectangle is going to look something like this. It's going to hit that line at some point xy. My goal is to maximize the area of the rectangle, so my objective function I want to maximize the area. And notice that for this rectangle, the length here would be the x value, and the width would be the y value. So the area of that rectangle would be x times y. All right, what's the constraint? Well, the constraint is that the point xy has to lie on this line, meaning that it has to satisfy x plus 2y equals 6. So let's solve this for x. It's just slightly easier because it doesn't require any fractions. X would be 6 minus 2y. And I'll plug that back into my objective function. And so my goal now is to maximize my area function. X I'm replacing with 6 minus 2y times y. So area would be 6y minus 2y squared. And if I do my first derivative test, a prime is 6 minus 4y. I'd like to know where that's equal to 0. So it looks like y is 1.5. I wanted the dimensions, plural, of my rectangle. I now know the height here, the width is 1.5, but I still need to know the x, the other dimension. So I'll plug back into my constraint. X is 6 minus 2 times the y of 1.5, which would be 3. So the dimensions of my rectangle would be 3 by 1.5. So in both of these last two problems, notice that we've used the equation of a graph itself as our constraint. That's something to watch for when you do these problems. All right, let's move on to example 6. An aquarium in the shape of a rectangular prism, just a fancy word for a box, is to be constructed as follows. The aquarium must hold, and I apologize, I keep meaning to fix that and I keep forgetting, 40 cubic feet of water. You can't have square feet of water. Right? The two ends of the aquarium will be square, and the cost of the material for the base is $3 a square foot. The glass for the sides is $2 a square foot, and then the ventilated top is going to cost $5 a square foot. Find the dimensions that will minimize the cost of the materials. So let's see what we've got. We've got our aquarium, which is the shape of a rectangular prism, or in other words, a box. And we do know that the ends of the aquarium are squares. So let's let the ends be x feet by x feet. Then this length in the front here can be y feet. So there's the diagram that shows my aquarium. And my goal, my objective function, is going to be to minimize the cost. All right, how am I going to write down a formula for the cost? Well, I'm going to have to figure out the cost of each side. So let's start with the base, the bottom. The bottom costs $3 a square foot. And notice I didn't put all the little dotted lines in here, but I could do that. The area of that bottom part would be x times y. So $3 a square foot for an area of xy. That takes care of the cost of the bottom. The glass in the front would be x by y, and that glass costs $2 a square foot, so 2 times xy. So let's just keep track here. This is the bottom, this is the front, and then the back would be exactly the same, right? So another 2 times xy. The right side is x feet by x feet. It's also glass at $2 a square foot. So 2 times x squared. And then the left side would be the same, so another 2 times x squared. Plus, I still haven't done the top. The top would be x by y, and it costs $5 a square foot. So 1, 2, 3, 4, 5, 6. I got all 6 sides of my aquarium, and their costs are all accounted for. Let's simplify that a little bit. Let's see, I've got 3, 4, 5, 6, 7, and 5 would be 12xy. And then I've got 4x squareds. All right, there's my objective function, but I still have too many variables, so I do need a constraint. And the piece of information that I haven't yet used if you look back in the problem, was the one I messed up, actually. We have to hold 40 cubic feet of water. So that's really saying that the volume of my aquarium is 40. And the volume is length times width times height. So that would be x times y, or x squared times y. And I could certainly solve for y here. Y would be 40 over x squared. So let's plug that into the objective function and say now my goal is going to be to minimize the cost function, which is 12x times this y, 40 over x squared, plus 4x squared. And that would be 480. That'll be x to the negative first, plus 4x squared. All right, I need to do a first derivative test. C prime is negative 480, x to the minus 2, plus 8x. And I'd like to know where that's going to be equal to 0. So I have negative 480 over x squared plus 8x equals 0. And I'm going to clear the fractions. I'm going to multiply through by x squared here. And let's see, I need a little more space here. So what do we get here? If I clear that fraction, I'll get negative 480 plus 8x cubed equals 0. 8x cubed equals 480. So x cubed is 60. And x would be the cube root of 60, or about 3.915. Once again, I'll leave it to you to verify that that really is a minimum. But I'm going to go ahead and finish this up by saying that means that the two ends of the aquarium are about 3.9 feet each. I still need the y value, which was the length of the aquarium. And I can get that just by plugging the 3.915 back into the constraint. So y would be 40 over 3.915 squared. And I get about 2.61. So the dimensions of my aquarium, again, remember that the y value is the length, the x's are the ends. I would have 3.915 by another 3.915 by 2.61. And these are all in feet. All right, we will pause there and come back and do a couple more examples in the next video.